Okay, Assalamualaikum warahmatullahi wabarakatuh. Today we will be dealing with chapter 4.9, which is a reduction of a simple distributed loading. So we are still in the chapter 4, where we mainly deal with moment. But at the end of chapter 4, we have this section where we deal with distributed loading, right? And in terms of the objective, it's for you to be able to deal with any distributed loading, because in reality, even though we have learned so far that for any structure we mainly have, or we have in terms of the drawing or the question, we have a single force here and then here and then here, etc. In real life it doesn't work that way, right? Because any object that have any weight, for example, it will have a distributed loading, for example, along that surface, right? So we have to deal with that. So this is, but we have to actually convert the actual distributed loading into just one single force in order to calculate the way we have been doing, right? So that's what this section is all about. It's how to reduce the distributed loading into one single force, and then we deal with it in terms of calculation of moment, calculation of force, etc., right? Okay, so in terms of application, you can look at the slide for 4.9, and the application is given there, some examples, right? So in many cases it's stated there that generally speaking we are dealing with distributed loading, and the type that we are dealing with specifically in this context, in this chapter, is where the problem can be reduced into 2D problem, right? Meaning that over the thickness, for example, there's this one on the surface, it will distribute force along this line, right? We're assuming that looking from here, it is evenly, the weight is evenly matched, meaning that here across the thickness, there's no distribution, right? It's a constant, right? So that it becomes a 2D problem, right? So that's basically the type of question that we will be dealing with, where it is a 2D problem, basically, right? And alright, so in that case we can have the distribution of the load is a function of length, right? So y in the function of x, right? Now for those who haven't covered yet, I have already posted early on a revision or crash course revision for integration, right? What you have learned before, but sometimes you have forgotten about it. You can refresh with that recording there. You can go there. And here and in some other later chapter, we will just pick up the integration part as a mathematical tool to calculate what we need to calculate, right? But in short, if we have a distribution where this is a force and then this is distance x, for example, right? It's clear, right? So if we have any distribution, for example, where we have all the forces going down, let's say, and with a function of, let's say, let's use y, for example, right? Y is a function of x, right? Whatever, for example, mx plus c, that is if it's a linear, right? So that's a function. So how to get the value here? Basically, the idea is something like this, right? We have covered simplification of force and further simplification, right, in 4.7 and 4.8. So the idea is something like this. So if we have some forces acting like this, let's say this is F1, F2, F3, where we have a distance D1, distance D2, distance D3, right? And if we have this, and to reduce it to just a single force here and a single moment here, this force Fr is simply just, in essence, the summation of all the forces, right? So it's basically, in this case, F1 plus F2 plus F3. Right, we have learned this before. And of course, this is just 2D and all the forces is in one direction, right? So it's simple. If you have x and y component, then you have to have the x component, y component summation, and then the f resultant is square root of fx squared plus fy squared. You have learned that before. Basically, it's a summation of force, right? And then this should be, the mr should be the summation of moment, or in essence, f1 times d1, this moment for this one, and then plus f2 times d2 plus f3 times d3, right? So it's the summation of each individual moment corresponding to each individual forces, right? And then if we further simplify to a certain force here, Fr, where we have a distance in d, let's say, so Fr is still the same, right? It's basically just summation of all forces, right? So in this case, from here to here to here, it should have the same impact or same effect on the beam, right? So we can jump also from here to here. The Fr is just summation of all the forces, right? And this d, we know that this distance is corresponding to this moment, meaning that Fr times d should equal to mr, right? Or in other words, d is mr divided by Fr, right? And mr we know is basically summation of moment, Fr is summation of all the forces, right? So essentially we can calculate for this location or this distance in 2D, if we have to say like this, is basically this distance is summation of moment divided by the summation of forces. So the concept is there, right? If it's 2D, if it's having S and Y component, if it's in 3D, the concept is still the same, right? So this position is what will cause the moment to be equal to the resultant of moment, right? Now, so the same concept here, right? Because distribution loading, here we have three forces basically, right? And distributed loading is basically just as if you have force in every every minute position, right? So that's the meaning of distribution, right? So the same concept applies. If you have distribution force like this and you want to replace with a single force, right? And to replace all of this with single force, there's two questions. One is, what is this force, right? And the second one is, what is this position or this distance? And that is simply just like this, right? It's the same. So force is just simply summation of all forces there, right? And in terms of integration, because this one is a curve, so in terms of integration, it's basically integration of dA, right? When you integrate dA, you get A, right? Because this is simply just the area under the graph, right? So the area under the graph will be giving you the force, right? What about this D? This D, if you understand that one, is just summation of moment divided by summation of force, right? And individually, if you consider this force here, and for each force there's a position, right, of x, right? So for summation of moment is basically simply integration of x dA, and then summation of f is integration of dA, right? This is an area in the graph because we will have the area, this one will have area times distance, where the area is force, force times distance becomes the moment, right? So the same concept there, right? So basically, if you have a distributed loading, this equation can be applied and you can integrate and you can get what is the force there and what is the distance there corresponding to any curve that you have, right? So that's the basic idea. Right? So if you have understood this one, you should be able to understand what's going on here, right? It's the same concept, right? And why do we need again to transfer here? Because for any given forces, basically if you do step by step, it's actually step before this one, right? If you have any distribution of forces, right? So you have to transform this distribution into single force at any particular point corresponding to this one, and then after that you can calculate the rest if you need to calculate this one, right? So that's normally how it is, or what can be the question in chapter 4, right? The question can ask you, get the equivalent force and couple moment acting at this point, and the question actually gives you in this form, right? So you have to have the step from here to here, and then from here to here, etc., right? But for point 9, actually we are dealing with the distributed loading to get into one single point force. All right, so let's see what else do we have. All right, now in the slide they give you 2 examples of basic shapes, right? If it's not a curve, it's just like a rectangle where the distribution is constant, or if you have a triangle, right? So let us see what will happen if we are applying this one for that kind of basic shape. So hopefully you have understood this one, so I'll erase this. Alright, so let's consider a rectangle, right? So meaning that if we have, let's say, distribution like this, right? And we want to replace it so that it will be just one force somewhere here, right? So let's give a certain value. So if I use an arbitrary value, right, or if I use the function, if we consider this to be L, this length to be L, and then for this one it is W. The function is y equal to W. Right? W can be any value, right? Y equal to 5 kilonewton per meter, etc. Right? So it's a certain value, but I'll just use W there, right, as a weight. So there's 2 questions here. One is the position, and one is the value of the force, right? So if you calculate the value of the force, so F is simply just integration of dA, right? And in terms of integration, so you have to have an element, like for example, if I have this element, if I take out the element, this one will be dx, and this one will be w in this case. So dA will be w dx, right, for that particular element. Obviously, if you need to refresh on the on the integration part, go watch the video I post early on crash course in refresh on integration, right? Anyway, so if you have that one, you plug in here, and what is the limit? Limit is from here to here, right? So from 0 to L, and dA is w dx. If you integrate that, you'll get wx, and then you have the limit of 0 to L, and then you get WL, right? So this is the force, and if you understand the concept, the force is the area under the graph, right? So this is calculation of area under the graph, but because it's a rectangle, so you can actually just calculate what is this multiplied by this one, right? That's the area under the graph, right? So you'll have W multiplied by L, which is the same. So this proves that it works, right? So of course, if the basic shape is just a rectangle, then for the force you just get the value multiplied by the length, you get the value, right? So in the example in the slide, it gives you like if W is 10 and then you have 5 meter, and then it will become 50 kilonewton, for example, right? That's about the value of here, right? So this one is just the height times the base, right? So W times L is basically the area for this particular case. What about the position, right? So if you want to calculate the position D here, is basically D is basically summation of moment, which is summation of integration of x dA over integration of dA, right? And we have already established what is dA. So you'll have integration of limit from 0 to L. You get Wx dA over integration of 0 to L W dA. Right? And if you proceed, you'll get Wx squared over 2 from 0 to L, and then it's the same there, right? Wx from 0 to L. So what you have here is WL square over 2 and then over WL. Right? So you cancel that, you get L over 2. Right? Is it still in the frame? Yeah. You get all L over 2. Basically it's halfway. So this one will become L over 2. Right? And logically you should be able to tell also, right? Meaning that if you have a rectangle, where should the force act on? It should be at the middle, right? Then it's a balanced position. So in the end, the idea is if you have a rectangle distributed loading, so it should be just the area, which is this one multiplied by this one, and then the position is exactly halfway. So half L here and half L there, right? So you can just memorize and apply it in the exam, right? But it's good to understand how we can prove that, right? Alright, that is if you have a rectangle. What if you have a triangle, right? So let us take a look at that. So let's say we have a triangle like this. So let's say we have a beam and a triangle like this, right? So if we imagine the slope to be what? Is slope to be like, for example, y equal to, because from the y equal to mx plus c, right? So if we assume the slope is 2, right? So let's say y equal to 2x, let us say, and then we just consider this to have the length of L, right? And if this is L and this slope is 2, even though this drawing is not logical, because slope of 2 you should have a steeper slope, but just as an example, then this one at the end here will be 2L, right? Meaning that if you have this function at x equal to L, y will be 2L, right? So that's just as a reference. Now, if you want to replace this with one force, right? So the first question is, what do you think? Is it that in the middle here, or more to the right, or more to the left? Logically, what will it be? It will be more to the right in this case, right? Because that's where most of the force, meaning higher force is there, lower force is here. Obviously, the average should be towards that way, right? Towards the higher side. So, but what is the distance, right? So we can put here, let's say F, right? Now, first in terms of the value, so F according to this one, so F is just summation of area under the graph or integration of dA. And if you take an element there, this one will be dx, this one will be y, right? So dA will be y dx. But of course, you want to integrate with respect to x, and y you can convert to x. So you'll get that dA is 2x dx based on y equal to 2x. So if you plug in here, you'll get 0 to L, dA is 2x dx. So if you integrate, become 2x squared over 2, 0 to L. Right? And then what you get, in this case basically you get L squared. Right? And again, we just want to check, right? We understand that we are calculating the area under the graph, and for a triangle where this is L and this is 2L, the area will be just half times this L times this 2L. what is this? Okay, sorry, this one will be 2L, right? So times 2L, and if you multiply that one, basically you'll get L square. Is it still in the frame? L square, right? So it should be the same, right? Meaning what you calculate here and what you calculate manually using just a triangle of half times the height times the base, you get the same thing, right? So it is proven, right? That's for the force. So basically this one is just half times this one and times that one, right? So obviously do not memorize. This is for your understanding, because this is if the slope is 2, right? If the slope is 1, then this becomes L, and you can recalculate and you should get the same answer whether you use half times base times height or you use integration, right? Because you are calculating the same thing using different method. So Sunnatullah, it should be the same, right? Now for the location D, so it is basically summation of moment divided by summation of force. Summation of moment is integration of x dA, over integration of dA, right? So dA we already have established to become 2x dx here. So in this case you have integration from 0 to L, x times that one, so 2x square dx over integration of 2x dx. So you get 2x cubed over 3, 0 to L, over 2x square over 2, 0 to L, right? So if you calculate this one, what do you get? So basically you get 2 over 3L cubed over this one cancel, so L square, right? So basically if you divide, you'll get 2 over 3L. So that's the length, meaning that this is 2 over 3L, right? Meaning that this remaining is 1 over 3L. So the ratio is like that. The ratio is 1/3 and 2/3, meaning that it's closer to the higher side and it's 1/3, 2/3 ratio, right? Just to check, right? If we have, let's say, the opposite triangle like this, right? Where in terms of the curve, let's use similar slope but the opposite slope. So you have y equal to negative 2x plus 2L, right? Because the intersection here will be 2L, right? So if you do that, and this is acting on a bar like that, and you want to know the force and the position. So in terms of the force, it's exactly the same, right? If you derive back in terms of integration of dA, you will get still the same value, right? Which means you get this one inside here, right? You get L squared, because you will get still if you have this L and this 2L, so half times L times 2L is simply L squared, right? So it's the same. Now, in terms of the position, so if you do this one, d equal to integration of x dA over integration of dA, right? So, and the dA is still the same, right? So if you take the element, it's still y dx, but yeah, but this one will be different, right? For this case, it's still y dx, but y is minus 2x plus 2L, right? So if you plug in here, or if you put it here, dA is actually minus 2x plus 2L, and then dx, right? Because y equal to all those expression there, so this function becomes here. So if you plug in here, you have integration from 0 to L, and then you get minus 2x squared, and then you have plus 2xl dx. On the downside here, so we have 0 to L minus 2x plus 2l dx. Right? And if you solve this integration, what you get is minus 2x cubed over 3 plus 2x squared over 2l from 0 to L over minus 2x squared over 2 plus 2xl from 0 to L. And then what you get here, this is enough space in this frame, right? So what you get here is basically minus 2 over 3 L cubed, and then plus L cubed. 2 over 2 is 1, so plus L cubed, and then over minus L squared, and then plus 2 L squared. Right, it will be something like that. So if you solve this one, minus 2 over 3 plus 1 or plus 3 over 3 becomes 1 over 3 L cubed. In this case, you get 2L squared minus L squared becomes over L squared. Right? And if you divide this, you actually get 1 over 3L. You get 1 over 3L. This is in this frame, right? So meaning that this distance here is 1 over 3 of this length, and meaning that the remaining is 2 over 3L. And as you can see, it is consistent, right? So the ratio is always 1/3, 2/3 of the length, 1/3, 2/3 of the length, but it will be closer to the higher side. For example, in this case, it will be closer to the right. So this is length is 1 over 3, and then this is 2 over 3. In this one, it will be closer to the left. So this is distance 1 over 3, and then that is 2 over 3L. Right. So this is just to show how we get for rectangular it's in the middle, for triangle it is 1/3, 2/3 ratio, right? So that's just the proof. And if you have shape like this, you can straight away just calculate the force is just the area, and then you just place 1/3 or 2/3 ratio like that, right? So you can do that. You don't need to actually derive and integrate for this particular chapter, right? But I'm just showing you anyway because this understanding you will have to know anyway for the purpose of chapter 8, chapter 9, chapter 10, for example, because you will be dealing with integration then, right? So it's good that if you refresh now and have become familiar with this. Alright. So in terms of the slide, you have the group problem solving, and we will try that one now. Alright. So should I redraw? I will try to redraw. Alright, so the question given in the slide, you can refer to the slide, of course, but I'll still try to draw this one here. So basically, you have something like a beam, and then you have the distribution, something like this, right, where the force is going down, where at the middle there is 6 kilonewton per meter, right? That is at the peak there. Obviously this is 0 and this is 0, right? And then you have 15 kilometer at the end, so you have a force here 15 kilonewton, and then you have 500 kilonewton meter there, so you have 500 kilonewton meter there. So the question says find the distributed loading on the given are the distributed loading, find the equivalent force and couple moment acting at point O. Meaning that in the end, I want to know what is this FR and what is this MR at point O. Is that the point O? Alright, so this is point O. So the question is exactly that. What is the equivalent force and couple moment at point O? So this and this. Right, so what to do? So again, hopefully you can imagine, first step is solving this distributed loading, and then when you have all the forces individually, you do the next step, which is getting the summation of FR and then summation of MR, right? So this one we can divide into two triangles, right? So this one is one triangle and this one is another triangle. If I take it separately, just for illustration, right? So for this triangle, the force should be 1/3 here, right? So this will be 1/3 of the distance. This should be 2/3 the distance, right? From our standing before, right? It's 1/3 to 2/3 ratio. In terms of the value there, it's basically just half times the height there, which is 6, and then multiply by, okay, I didn't put the distance, so it should be put there also, right? So the distance is 7.5 meter until the middle, and then 4.5 meter. Alright, so for this triangle, the base is 7.5, so meaning that I know this one will be 5 meter, this one will be 2.5 meter, right? Giving 7.5 meter. So that is basically it. So the value is, okay, sorry, this is half, I didn't finish this, half times 6 times 7.5. Alright, so that's the missing value, because I forgot to also draw the distance. So when you get the distance, so height times base, you get that one, and then this is just 1/3 to the ratio, right? And for this one, for this triangle, then you know obviously this should be 1/3 ratio here, 2/3 of the length there, right? So that's number one. In terms of the value, is just half times base times height, so it's half times 6 times 4/5. That's basically just half times this, right? The base times the height. Once you get that one, you can actually plot the original question back again, where you have this one doesn't change, 15 kilonewton, and this one is also doesn't change, and in this case, 500 kilonewton meter, right? And what changes is this two triangle, right? So this one becomes just one force here, with the value there, 1/2, 6, 7.5, and then the distance will be, what will be the distance? The distance will be this one, right? 2/3 of the length of that one, so 5 meter. Hopefully you're still following. And then for this one, we have another force here, where the value is half times 6 times 4.5. The distance will be what? Here it will be 1/3 of the length, which will be, based on this 4.5, this will be 1.5 meter, and this one will be 3 meter, right? So based on that 1.5, the distance throughout total will be 7.5 plus 1.5 becomes 9. 9 from the end, right? So 9 will be here, 9 meter, right? So what to do next? So it's basically just simplify into one single force, right? So we want to simplify into point O, right? Find the equivalent force and couple moment at point O. So that is basically what it means. So we want in the end is just Fr, and then what is moment, right? So how to get this Fr is simply just adding all of this, right? So half times 6 times 7.5 plus half 6 4.5 what is next, plus 15, right? So that's basically the summation of all forces acting downwards, right? And I'm saying this to have positive downwards. What about moment? Moment is just simply, okay, what is this total distance? It is 13, is it? Meaning the total distance here is 13. Right, if I have correctly. 7, 8, 9, 10, 11, 12. Right? 12. What do you call it? Not 12, 13. Is it 13 or 12? 7, 8, 9, 10, 11, 12. Right? So the distance is 12. How did I get 13 just now? So it is 12. In terms of moment, right? This moment is just summation of moment, right? So basically, if you take from here, it becomes 15 times 12, and then we get here, we get plus half times 6 times 4.5, and then times the distance of 9, right? And then plus again, this one is half times 6 times 7.5 with the distance of 5. So you can calculate, right? What is the summation of moment? So basically just add them all together. Right? So that's basically how you answer that question, right? So, okay, sorry, I have forgotten to add another one. So we have computed this one, 15 times 12 distance, this one times 9 distance, this time 5 times 5 distance. So, one thing that is forgotten here is plus 500. 500,000, not 500 kilo. Why? Because this one is rotation clockwise, so it matches here, rotation clockwise. Yeah, so that's basically how you calculate it. Right. And you can see the answer in the slide. You get Fr equal to 51 kilonewton, and then you get couple moment at point O is 914 kilonewton. Right, so you can verify your answer, or even my answer if I have done any mistake. Right, please point out as such. So in terms of the slide itself, in terms of the lecture, we are out of slide, meaning that that's the end already, right? There's only one example how to apply this one, and hopefully you understand, right? So basically what we want in the end in this particular question, it depends. The question sometimes can ask further simplification, which is just one force here and a distance, right? That's also not that difficult, right? But it's a bit longer, that's all. So basically what you do is you divide the area, get the force of each area, right? And of course the original force and moment should be there still, and then you just calculate summation of force and summation of moment, right? So that's about it. And some other examples other than this one is going to be covered in the class, inshallah. If you have any question anyway, please take note where is the question from, what is the number, etc., and do ask in the class, right? I'm there to help, inshallah, all my best, right? So with that, I think we wrap up chapter 4. That's the end of chapter 4.9, marking the end of chapter 4 as a whole, right? So next recording, next video will be for chapter 5, inshallah. Yeah, so it's already 1:29 a.m. in the morning, in the middle of the night basically. So we end the session here. Subhanakallahumma wa bihamdika, ashhadu an la ilaha illa anta, astaghfiruka wa atubu ilaik. Wassalamu alaikum warahmatullahi wabarakatuh.